Prime numbers are these abstract, mysterious things. They're the atoms of arithmetic. Lots of the most basic questions about prime numbers remain unsolved today, even if they've been studied by the greatest minds in mathematics for hundreds or thousands of years.
In the summer of 2020, an undergraduate at the University of Connecticut plotted some numbers on a screen for a homework assignment.
We have theories about what kinds of capabilities these systems will have. That's obviously what we try to build into the architectures. But at the end of the day, how it learns, what it picks up from the data is part of the training of these systems.
He thought the job was boring. Instead, the dots on his graph started to swirl like a flock of birds in flight. And what he had stumbled into would shake the foundations of mathematics, force the smartest artificial intelligence on the planet to play catch-up, and reopen the oldest unsolved problem in the world. The year everything changed. In the spring of 2026, mathematicians around the world started saying something out loud that they used to whisper behind closed doors. Artificial intelligence is no longer just helping with math. It is doing math. And the speed of what is happening right now is leaving even the smartest people in the field stunned and a little nervous. Earlier this year, a team at Google DeepMind announced that their newest system, called Gemini Deep Think, had solved 4 open problems from the Paul Erdos Problems database without any human guidance. These were problems posed by Erdos himself, one of the most legendary mathematical minds of the last century, a man who traveled the world with nothing but a suitcase and an obsession with finding the most elegant proofs of the hardest conjectures. The problems he left behind had sat in his archive for decades, taunting his fellow mathematicians. The artificial intelligence did not just guess at the answers. It produced rigorous, formal proofs that real human mathematicians could check line by line and verify against the rules of logic. Then, in January of 2026, a different system at the same lab, called AlphaEvolve, was set loose on a problem in algebra. It found hidden structures inside something called Brouhat intervals, structures that had been sitting there for 50 years right under the noses of the world's top algebraists. Geordie Williamson, the Australian mathematician who collaborated with DeepMind on the project, told Quanta magazine that he could not believe what he was looking at. He said the pattern had been there for half a century, and nobody had ever spotted it. He also said that with these new tools, he could now do experiments in 20 minutes that 2 years ago would have taken him 2 weeks of hard work. The biggest breakthrough in modern number theory in the last 100 years did not come from DeepMind. It did not come from Princeton or Harvard or Cambridge. It did not come from any place with $1 billion in funding and a glass office in Silicon Valley. It came from an undergraduate student at the University of Connecticut, sitting at a desk during the summer of 2020, working on a homework assignment that he honestly thought was a waste of his afternoon. What that student plotted on his screen would soon force Princeton mathematicians to sprint to catch up to him. It would send the most prestigious institute for advanced study in the world into a frenzy of new papers and new conferences, and it would expose a pattern hidden inside the deepest building blocks of mathematics that the entire history of human thought had completely walked past. He named what he found after a flock of birds, and that name has stuck ever since. The real story is that the most resistant problem in the entire 2,000-year history of mathematics is finally starting to crack. The first crack came from that undergraduate. His name was Alexei Postnyakov, and his professor took one look at the screen, went silent, and knew that whatever the kid had just done was going to make the textbooks. The problem that beat 2,000 years of geniuses. In November of 1859, a quiet German mathematician named Bernhard Riemann sent a short paper to the Berlin Academy. The paper was only 8 pages long, but it would haunt mathematics for the next 167 years. In that paper, Riemann was trying to solve a question that had bothered every great mathematical mind for over 2,000 years. Why do prime numbers behave the way they do? And why does nobody seem able to predict where the next one will appear? You learned about prime numbers in school, even if you have forgotten most of it by now. A prime number is any whole number greater than one that you can only divide evenly by itself and by the number 1. Some examples include 2, 3, 5, 7, 11, 13, and 17, and the list continues forever. They are the building blocks of every other whole number in existence. Every number that is not prime can be broken down into primes that multiply together to make it. That is why mathematicians call primes the atoms of arithmetic. They are the foundation of everything else. The strange thing about primes is that they go on forever. The ancient Greek mathematician Euclid proved this fact over 2,000 years ago, and his proof still works today. There is no biggest prime number. They keep showing up no matter how far you walk along the number line. But here is where it gets weird. Nobody can predict where they will show up. 2 and 3 sit right next to each other. Then there is a gap of 2 until you reach 5. Then a gap of 2 again to 7. Then a gap of 4 until 11. The gaps grow, they shrink, they swing around, and the whole sequence looks like somebody threw the primes onto the number line with their eyes closed. This bothers mathematicians on a very deep level. Mathematics is supposed to have structure. 2 plus 2 equals 4 in every universe and under every physical law. Mathematics is the one place in our reality where order is supposed to be guaranteed, except for the primes, which seem to break every rule we try to apply to them. That chaos has been the single most embarrassing problem in the field for centuries. Carl Friedrich Gauss, the man often called the Prince of Mathematics, spent years working on prime distribution in the late 1700s. He came up with a rough formula that estimated how many primes you would find below any given number. The formula worked, more or less, but it was still just an approximation. It was a best guess. It was not an explanation, and best guesses are not good enough for mathematicians. Then Riemann came along. Instead of trying to count primes directly, he invented a strange new object called the Riemann zeta function. The function takes a complex number as input and gives a complex number as output. When Riemann looked at the places where his function equaled 0, he noticed something extraordinary. All of those zeros seemed to fall on a single straight line in the complex plane. He could see this pattern in his calculations, but he could not prove that it would always hold. So he wrote it down as a hypothesis and moved on with his life. That hypothesis became the Riemann hypothesis. It is now the most famous unsolved problem in all of mathematics. The Clay Mathematics Institute will pay $1 million to anybody who proves it, and that money has been sitting unclaimed since May of the year 2000. Since Riemann's time, mathematicians have used computers to check the first 10 trillion zeros of his function, and every single one of them lies exactly on the critical line. But nobody has ever been able to prove that the 10 trillion and first zero will behave the same way. That gap is the gap that has resisted some of the greatest minds in human history. For 113 years after Riemann published his paper, nobody got anywhere close to cracking the hypothesis. Then, in the spring of 1972, two strangers met for tea at Princeton, and the world quietly tilted on its axis. The most famous cup of tea in mathematics. In April of 1972, a young American mathematician named Hugh Montgomery walked into Fuld Hall at the Institute for Advanced Study in Princeton, New Jersey. He was carrying a piece of work that he was quite proud of, work that he had spent months developing. Montgomery was studying the gaps between the zeros of the Riemann zeta function, the same zeros that Riemann had noticed lined up on his critical line over a century earlier. Montgomery had derived a formula that described how those zeros were spaced from each other. It was the kind of result that would normally just sit in an academic journal somewhere and be cited by other specialists. He had come to Princeton specifically to talk to Adlai Selberg, one of the great living number theorists of the time. But before he got to Selberg, somebody else stopped him in the common room. That somebody was Sarvadaman Chawla, an Indian mathematician who was visiting the institute. Chawla took one look at what Montgomery was working on and insisted on introducing him to another visitor in the room, a tall and soft-spoken physicist with sharp eyes and a quiet Englishman's manner. That physicist was Riemann Dyson. Dyson was not a number theorist. He was one of the most respected physicists in the entire world, a man who had helped lay the foundations of quantum electrodynamics in the 1940s. But he was curious about everything, and Chawla insisted that he look at the young Montgomery's formula. So Montgomery walked into a blackboard and wrote it down for him. The formula was a complicated expression involving the gaps between the zeta zeros, an expression with sines and pi, and a fraction that took a moment to parse. Dyson read it once, read it twice, and then he said something that nobody in the room expected him to say. He told Montgomery that he had seen that exact formula before. He had seen it in his own work on heavy atomic nuclei. The formula that described how the zeros of Riemann's function were spaced was the exact same formula that described how the energy levels of large atoms behaved inside their nuclei. The mathematician Andrew Odlyzko, then working at the famous Bell Laboratories in New Jersey, spent the next 2 decades testing the connection on a computer. He calculated millions of zeros, then billions of zeros, and the match between Montgomery's formula and Dyson's nuclear physics held up perfectly. By the late 1990s, the connection had earned a name. They called it the Montgomery-Odlyzko law, and it was one of the strangest results in the history of science. But there was a serious problem with the discovery. Knowing that the pattern existed was not the same as knowing why it existed. Mathematicians had a clue, a fingerprint, a deep hint that something profound was going on inside the primes. But they could not crack the actual structure underneath. They could not see the shape of the thing they were chasing. For another 50 years, the Montgomery-Dyson connection sat in mathematics like a locked door with no key. Everybody knew it was there. Nobody could get through it. The key would eventually come, but it would not come from a famous laboratory. It would come from a college kid in Connecticut who did not even know he was holding it. The intern who saw what nobody else could. In the summer of 2020, while most of the world was locked indoors trying to figure out what month it was, a young man named Alexei Pozniakov was working on a summer research project at the University of Connecticut. He was an undergraduate. He was not famous. He was not a Fields medalist. He was just a kid with a laptop and a curiosity that would soon shake the entire field of number theory. His supervisor was a mathematician named Q-Hwan Lee. Lee had been working with 2 collaborators, a physicist turned mathematician named Yang Hui He at the London Institute for Mathematical Sciences, and a number theorist named Thomas Oliver at the University of Westminster. The 3 of them were interested in a particular kind of mathematical object called an elliptic curve. Elliptic curves look simple from the outside. They are described by short equations that you could write on the back of a napkin. But they are the secret backbone of modern cryptography, the same cryptography that protects your bank account, your email, and your phone right now as you watch this video. Lee gave Pozniakov a fairly boring task to complete. He wanted the undergraduate to feed a bunch of data about elliptic curves into a basic machine learning model and see if the model could classify the curves by something called their rank. The data came from a famous online database called the L Functions and Modular Forms database, run by Andrew Sutherland at the Massachusetts Institute of Technology. That database contains information on millions of mathematical objects, all carefully verified and freely available to researchers everywhere. Pozniakov ran the model. It worked. The classification went better than he expected, which made him pause and look closer. He decided to plot the inputs of the model on a graph, just to see what they looked like with his own eyes. He averaged out a particular kind of number called the Frobenius trace across many elliptic curves, and he plotted those averages against the primes. He hit the Enter key, and what came up on the screen made him sit back in his chair. The dots did not scatter randomly across the graph. They did not form a straight line. They did not behave like noise. The dots curled and swirled across the screen in the shape of a flock of birds in flight. They formed rolling, rippling waves that moved together in patterns nobody had ever recorded before. They flocked. Thomas Oliver later told Quanta magazine that when Alexei showed the team the picture, the first thing he said was that it looked like that thing birds do when they fly together in the evening sky. Hugh Huan Lee looked the word up, and the term for what birds do when they swirl through the air in those shapes is murmuration. Yang Hui. He took one look at the image and said the paper had to be called Murmurations of Elliptic Curves. The paper was posted online on the 21st of April, 2022. It described a pattern that nobody had ever seen in the building blocks of number theory. The pattern was not visible if you looked at one elliptic curve at a time. It only revealed itself when you averaged thousands of them together. It was a statistical fingerprint hiding in plain sight, in data that mathematicians had been staring at for decades without ever noticing what was there. Pozniakov himself later said that, at first, he was just happy he had completed the assignment. But Lee immediately knew that what they were looking at was something special, something that should not have been there, something that the entire history of mathematics had walked right past without ever giving it a second look. Within months, the murmuration had reached Princeton, and a graduate student there was about to do something that would force the entire community to admit Alexei had cracked open a door that nobody knew existed. The mathematicians who cracked the code of the birds. The Pozniakov paper hit the number theory community like a small earthquake. Within months, mathematicians at the best institutions in the world were trying to figure out what the murmuration actually meant. The pattern was real. That much was clear to everybody. But why was it there? What did it tell us about elliptic curves, about prime numbers, and about the deeper structure of mathematics itself? The first major breakthrough came from a young graduate student at Princeton named Nina Zubrilina. Zubrilina was working under the supervision of Peter Sarnak, one of the most respected number theorists alive today, and a senior figure at the Institute for Advanced Study, the same institute where Montgomery and Dyson had met for that fateful cup of tea 50 years earlier. Zubrilina decided that she was going to prove the murmuration existed, not just observe it from a distance. She picked a slightly different setting from the one Pozniakov had used. Instead of looking at elliptic curves directly, she looked at something called weight-2 new forms, which are close cousins of elliptic curves in the world of number theory. In October of 2023, she posted a preprint to the public archive showing that she had derived a formula for the murmuration density, a clean and exact mathematical expression that described why the dots flocked the way they did and how the pattern unfolded as you moved up the number line. Peter Sarnak told Quanta magazine in March of 2024 that Nina's achievement was that she had given a formula for the phenomenon. He called it the Zubrilina murmuration density formula, and the name stuck in the community immediately. But Zubrilina's formula was only the beginning of the avalanche. In April of 2025, two more mathematicians named Will Sawin and Andrew Sutherland posted their own paper to the archive. Sawin is based at Columbia University in New York. Sutherland is at the Massachusetts Institute of Technology and runs the same database that started all of this in the first place. The two of them used a deep tool from analytic number theory called Voronoi summation, and they extended the murmuration result to elliptic curves ordered by what mathematicians call their height. In plain language, they proved that the murmuration is not a fluke. It is not an artifact of one particular way of looking at the data. It is real, it is universal, and it shows up across the entire landscape of L functions, the family of mathematical objects that includes the Riemann zeta function itself. The L functions that the murmurations live inside are the same family that Riemann was studying when he wrote his hypothesis in 1859. The pair correlation pattern that Montgomery and Dyson saw at T is part of the same web. And now, thanks to one undergraduate plotting some dots in a bedroom in Connecticut, mathematicians have a new kind of pattern, a new fingerprint, and a new way to peek at the hidden structure that controls the primes. Yang Hui. He told the London Institute for Mathematical Sciences that artificial intelligence had revealed correlations among elliptic curves which he called murmurations, and that those murmurations expose hidden symmetries in number theory with possible applications in cryptography and cybersecurity. He was being polite. The truth is that nobody yet knows how deep the murmuration phenomenon actually goes. Some mathematicians believe it could provide a new path toward the Riemann hypothesis itself. Others believe it could rewrite parts of the Langlands program, the most ambitious project in modern mathematics, a grand unified theory of numbers that hundreds of researchers have been working on for over 50 years. While Princeton, MIT, and Columbia were racing to catch up to a college kid, Google DeepMind was watching the whole thing from London, and what they decided to do next would change the conversation about artificial intelligence and mathematics forever. The lab that came late to the party. For a long time, Google DeepMind has been the most famous artificial intelligence laboratory on the planet. The company was founded in London in 2010, and Google bought it in 2014. Then, in April of 2023, Google merged DeepMind with its other major artificial intelligence research team, Google Brain, into a single organization led by Demis Hassabis. The combined unit has been on a winning streak ever since. DeepMind's first big move into pure mathematics came in December of 2021, when they published a paper in the journal Nature alongside two senior mathematicians, Mark Lackenby of Oxford and Geordie Williamson of the University of Sydney. The paper described how a machine learning system had helped the human mathematicians discover a new connection in knot theory, specifically between a geometric measurement called the natural slope of a knot and an algebraic invariant called the signature. It was a real and original contribution to the field. The DeepMind researcher Alex Davies told reporters at the time that nobody had ever used machine learning to make significant new discoveries in pure mathematics before that moment. Then came FunSearch in December of 2023, a system that paired a large language model with an evaluator to find new solutions to old combinatorial problems. The DeepMind vice president, Pushmeet Kohli, told MIT Technology Review that the solution FunSearch produced for the CAPSET problem was not in the training data, and it was not even known before by anybody in the field. In 2024, DeepMind's AlphaProof system won a silver medal at the International Mathematical Olympiad, solving 3 problems, including the famously difficult Problem 6. Then came AlphaEvolve in 2026, the system that found those hidden hypercube structures inside Bruhat intervals that I mentioned at the start of this video. So DeepMind has been doing real, serious, original mathematics for years now. But here is the part that the breathless headlines have not been telling you, my friends. DeepMind has not, as of this moment, cracked the Riemann hypothesis. They have not found a hidden pattern in prime numbers that proves the hypothesis is true. They have not embarrassed the global mathematical community by showing them a secret that 2,000 years of human thought had missed. The story of the murmurations was never their story. It was Alexei Pozniakov's story, and the people who are now extending that story, Zubrilina at Princeton, Sawin at Columbia, Sutherland at MIT, are mostly working with their own tools, their own graduate students, and their own ideas. That has not stopped DeepMind from getting interested in a serious way. In October of 2025, the company launched something called the AI for Math Initiative, partnering with the Institute for Advanced Study, Imperial College London, the Simons Institute at Berkeley, and 2 more major research centers around the world. The goal is to use artificial intelligence as a serious mathematical collaborator across the entire field. The closer DeepMind gets to the world of L functions, primes, and the Riemann hypothesis, the more nervous one specific group of people becomes. That group is the cryptographers. Here is the reason for their nerves. Every time you log into your bank account, every time you send an encrypted message, every time your phone connects to a secure server, you are betting that prime numbers are hard to predict. The most common form of Internet encryption, called RSA, after its inventors Rivest, Shamir, and Adelman in 1977, is built entirely on that single bet. If somebody, or some machine, finds a deep pattern in primes, that gives away their underlying structure, the entire foundation of the digital economy starts to wobble. The United States government has been preparing for this possibility for years. In August of 2024, the National Institute of Standards and Technology released the first 3 official post-quantum cryptography standards. The National Security Agency has set a series of strict deadlines. All new national security systems must use the new quantum resistance standards by the 1st of January 2027. Legacy equipment must be phased out by 2030, and full quantum resistance must be in place across all critical systems by 2035. Trillions of dollars in critical infrastructure is being quietly rebuilt right now, because the security people are not waiting around to find out if Pozniakov, or Zubrilina, or Gemini DeepThink stumbles onto the next murmuration. The deepest question, though, is not whether artificial intelligence will break encryption. The deepest question is something much stranger, and it is something that should keep you up at night if you stop and really think about it. The mirror that mathematics holds up to us. For over 2,000 years, mathematicians have argued about a question that sounds simple but turns out to be impossible to settle. Is mathematics something we discover, or is it something we invent? The philosopher Plato, writing in ancient Greece, believed that mathematical objects are real in some fundamental sense. He thought that numbers, circles, and triangles exist in some perfect and eternal realm, and that human mathematicians are explorers who travel to that realm and bring back maps for the rest of us. When Riemann saw his zeros lining up on a critical line, he was not creating that line. He was finding it. The line was already there, waiting for him to arrive. For most of history, the debate was just a philosophical curiosity. Mathematicians did their work, philosophers did their arguing, and the two groups mostly stayed out of each other's way. But the murmuration story has put a strange new pressure on the question. Here is the thing, my friends. The murmuration was real. It existed in the data. It was sitting there in the Massachusetts Institute of Technology database for years before Alexei Pozniakov ever opened his laptop. Andrew Sutherland and his colleagues had been adding to that database for decades. Mathematicians around the world had been studying elliptic curves and L functions since the 1800s. The pattern was there the whole time, and nobody saw it. The English mathematician G.H. Hardy wrote in 1940 that a mathematician is, above all, a maker of patterns. He believed that mathematical truth was discovered and not invented. But Hardy could not have imagined a world in which a non-human intelligence sees patterns that no human can see. He could not have imagined Gemini DeepThink solving Erdos problems while a teenager somewhere is doing the same thing with a laptop on his kitchen table. Demis Hassabis, the head of DeepMind, has been honest about how far the technology still has to go. He told the podcaster Lex Fridman in 2025 that today's systems cannot yet do the kind of imaginative leaps that Einstein made when he came up with special relativity. The mathematician Terence Tao, on the same podcast a few weeks later, said the truly hard problems, like the Riemann hypothesis and the twin prime conjecture, are still very much open and far from solved. None of this is over. But the door is open now in a way that it never was before. The murmuration was just the first thing through that door. There are almost certainly more patterns, more fingerprints, and more flocks of birds hidden inside the data that humanity has been quietly collecting for centuries. The next time one of them is found, it might not take a college student or $1 billion artificial intelligence. It might take both of them working together, looking at a problem that has been sitting in front of us in plain sight the whole time. Mathematics has been holding up a mirror to us for 2,000 years. We are only just now starting to notice what is in our own reflection. Drop your thoughts in the comments below and let me know what side of the discover or invent debate you fall on.